This video is entitled Tangent Plane and Normal Line to a Surface. Alright, as mentioned in the directional derivatives video, that you can't have a unique tangent line on a three-dimensional surface because technically would be infinite tangent lines. So in single variable calculus, yeah, we could have a tangent line to something like this, at a point, maybe look like this. That's not very good, obviously, but it's supposed to be touching right there. But you can't have a unique line in three-dimensional shapes, but you can have what's called a tangent plane. In other words, you can have a plane there in blue that touches only in the immediate area at the point you're trying to find this tangent plane. So obviously, just like in two-dimensional graphs, if the graph came out and changed shapes or whatever, yeah, the plane could hit it again, out in the distance. But it just means at this particular point, it's only hitting it here, and in the immediate, it's not touching it anywhere else in the immediate area. So we can find tangent plane. And this is just the definition of the tangent plane. And then we have something called the normal line, which the normal line would be the equation of the line that comes out 90 degrees to the plane. Of course, there will be a vector there, but then to come up with a line, we have to, use ideas that we learned earlier on in the course involving how to come up with the equation of a line in 3-space. I believe that section was called Lines and Planes in Space. Alright, let's try this out here. Equation of a tangent plane. Now similar, we had the idea of a tangent plane way back in that same section I just mentioned, where you had A, B, and C were the values in front of this x minus x0, y minus y0, and z minus z0. So let me come back up here for this figure just for a moment here. So obviously we need a point, and then we need a normal vector to that plane to be able to come up with the equation of that plane. Well, in the sections of directional derivatives and gradients, we learned that the gradient, by definition, the gradient, which is a vector, is the normal vector at a particular point. So therefore, if it's a normal vector at a point, it'll be a normal vector to that plane. So that's what these coefficients now are. They represent the values of the gradient. So it's the fx, fy, fz partial, which like here I see I've written right there, just kind of equate to what it used to look like there. So that would be essentially your ABC. So really it's the same equation, it's just using the gradient to come up with those values ABC. So that's the key. Your normal vector is the gradient. Then we can go from there. So that's good. Now, the normal line, I'm not going to worry about symmetric form. I'm only going to consider this parametric form here. I don't really like the symmetric form as much, but so we have x equals. So once you have the gradient, you can also use it here too, because the line will be heading in the same direction as the gradient vector will be. So it's the same ABC right here. So that's the same equation we had before: x equals x0 plus at, y equals y0 plus bt, and then z equals z0 plus ct. So this isn't too difficult. Let's try this out. In fact, notice this example right here I took out of this textbook. I immediately got rid of the word symmetric and changed it to parametric, because that's the way I would ask it. So let's see what we have here. So we have to make sure it's in implicit form here is all. You can bring the 9 over if you want to. That doesn't matter as long as the variables are all on one side. We're good. that's technically good enough for an implicit form. But if you want to, we did some stuff earlier where we have to set it equal to, 0 with the chain rule stuff. But it didn't matter then either, whether I bring the 9 over or not, it's going to work the same. So it's already kind of set up for us here. We're in good shape. All right, super duper easy gradient here. So the partial, x partial will be 2x, y partial will be 2y, z partial will be 2z. And then the point is 1, 2, 2. So I plug 1, 2, 2 into the gradient, which is my n, my normal vector for the plane, will be the gradient. And it's just going to double everything, so it makes it 2, 4, 4. So to get the equation of the plane, here we go. So the fx, fy, fc that we just found right here, those are in front of each parentheses. So it would be 2 times x minus 1, because the x is 1, plus 4 times y minus 2, plus 4 times z minus 2. Now, in a handwritten form, obviously this is an acceptable answer here, but possibly on a quiz or a multiple choice exam, you may need to distribute that out, but that's pretty simple algebra. If you just distribute that out, and I move the number to the other side, and then, which this is correct, but I also noted that, they may reduce it if it can be reduced, and it can. Since you could multiply both sides by 1/2, it would just be like dividing everything by 2. So this is correct, but then you might be looking for this. X plus 2y plus 2z equals 9 would be the tangent plane at that point of that curve, of that graph, which that graph is a sphere, by the way. Now, the parametric forms of the line, no problem. So the x0, y0, z0 would be 1, 2, 2. So we go straight down the line, 1, 2, 2. And then my gradient values, the same ABC for the line as it was for the plane, would be 2, 4, 4. So there's your set of parametric equations that would graph that line, going the same direction as that vector. Oh, looks like I graphed it. All right, so yeah, see, it was a sphere. And then the green part represents the tangent plane, and then there's the line coming out of it. So obviously I typed in everything we got above as the answer, so it wasn't like a built-in function that graphed all this. It was based on what I told it to graph. But that looks pretty good. I like it. So there's that tangent plane at that point, and there's that line shooting out there 90 degrees. Excellent. Now let's see what we have. Now here's one that's in explicit form that we need to convert to implicit form. So you see the f of xy is z, so I brought the z over and made it negative z right there, and then wrote it like, remember the big F, capital F, means implicit form. So big F of xyz gives you this equation. So I bring the z over, makes it capital F. You can do it without doing that, but if you do it this way, you only have to use one formula, you don't have to really come up with a different way to do this. So it's totally worth it to move that z over there. So let's look at my partials to lead to our gradient. So the x partial would be 2x minus 2y. The y partial would be negative 2x plus 2y. And then the z partial would be negative 1. So I need to plug in the point 1, 2, 1. So I'd have, what would this be? 2 times 1 minus 2 times 2 is negative 2. Minus 2 times 1 plus 2 times 2 would be positive 2. And then that's constant at negative 1, so there's nowhere to plug any values in there. So we have our gradient vector is negative 2, 2, negative 1. So as you can see, that's my coefficients here in front of each parentheses. Negative 2, positive 2, negative 1. And my point, we'll see, was 1, 2, 1. Oh, I guess I already had it. I already had it right here. I didn't have to scroll back up there. But anyway, so it's negative 2 times x minus 1 plus 2 times y minus 2 minus 1 times z minus 1. Once again, I flag that as being that's correct mathematically, but just in case you had to distribute this out, you can do this. Also, another thing to keep in mind, not only did I mentioned earlier about what if it has a common multiple. Well, that multiple could also be negative 1. So that means you're looking at this and you're trying to match an answer on a quiz or a test, and you think, oh no, my answer doesn't seem right. But if you multiply everything by negative 1, meaning you change all the signs, you might see an answer that says 2x minus 2y plus z plus 1 equals 0. Or it could have the 1 over on the other side and make it negative 1. So if it has all the opposite signs, that means it's the same answer because it's the same as multiplying by negative 1. And then 1, 2, 1 here for the normal line would be your starting coordinates, x0, y0, z0. And then you have negative 2, positive 2, negative 1 as your gradient. And that's your direction vector for your line. So it'd be 1 minus 2t, 2 plus 2t, 1 minus t. And then so the point is 1, 2, 1 right there. Out 1, over 2, up 1, so it's right there. So you see there's the tangent plane in green. So it looks like that's clipping alongside it pretty well there. I like that. And then there's the normal line shooting right out of it. All right, not too bad. Obviously, you're never responsible for the graphing, but I think it's interesting to look at, see what we just did there, basically. So, all right, now we have another one, equation of a tangent plane at the point 1, 2, 1, and the normal line. That's a weird looking little function there. That's okay. So just bring the 3 y squared z cubed over, make it negative. You can leave the negative 6 where it is. So I have to take 3 partials now. Let's see. For x, y, and z. So for the first one, I'd bring the 3 down, like I did here. Change the power to 2. And then the derivative of the inside with respect to x would be 2x. Come over here. This partial with respect to x would be, bring the 2 down, makes it negative 2xy. There's no x here, so don't have to worry about that. So there's your fx. Fy would be, don't have to worry about the first one. The derivative of y is 1, so it makes it negative x squared. And then the derivative of negative 3y squared would be negative 6y, and with the z cubed, so it's minus 6y z cubed. Then I come down here. For z, bring the 3 down, change the power to 2. The derivative of the inside is 2z, like so. All right. And then the middle term doesn't have a z, so we come over here. 3z squared multiplied by this makes this negative 9y squared z squared. So there's our gradient. Put in 1, 2, 1 into each of these. Just plug the numbers right in there, and you should get 20. Negative 13, negative 30. That will be my normal vector for the plane. Gradient vector, which is also the normal vector. And then my point was 1, 2, 1, so it'd be 20 times x minus 1, minus 13 times y minus 2, minus 30 times z minus 1, equals 0. And then the lines of the point 1, 2, 1, and then there's the coefficients of t. Same as this, 20, negative 13, negative 30. Now this one, I did not, I graphed it down here. I did not, I guess for some reason I didn't distribute all this out, so, but just keep in mind, like the other 2 examples there, that you may have to distribute that out to put it in, I think this is called standard form, and the other one's called general form, but that's okay. You don't have to know it by name, it's just recognizing how they have the answer expressed. If it's just like this, then you would be done. And it looks like I took a graph of that one there too. Let's see. Well, looks like a couple of little, that graph generates a couple little opposite paraboloid looking deals there. There's the point. I made the dot real big there. Big old dot. There's the tangent plane at that point. 1, 2, 1, I guess it was. 1, 2, over 1, up 2 over 2 and up 1 on the z-axis. And there's the line coming right out of it. Very good. All right, so now we have a new idea to learn in this section. It's not too bad. We have what's called angle of inclination. In other words, at what angle that a plane is elevated from the XY plane. And this will be measured as the angle's got to be between 0 and 90. So it's kind of like using the same angle. What we're doing essentially is we're to find the angle between these two planes, we find the angle between their respective normal vectors. Because if you think about it, see, the normal vector is 90 degrees to the plane. So if both normal vectors are 90 degrees, in respect to their planes, that means the angle between those two normal vectors will be the angle between the planes. So you see these two, this theta right there between those vectors is exactly the same as that theta right there. Because like I said, everything just shifts over 90 degrees. Now we have an absolute value here to protect this, to make it positive, so it'll be between 0 and 90. Now this is different than just the angle between two vectors in general, because let's say, I'll just kind of make a rough sketch here. You could have a vector like this, and you could have a vector like this, and then we could find that, and that would be somewhere between 90 and 180. So it was possible for those angle between two vectors to be something that's not between 0 and 90. But the idea behind this is you really, it's not, one of them's the XY plane. So what you're really doing is, you're finding the whatever the shortest distance to the XY plane is. So in this case, it wouldn't be this angle right here. It would be this angle right here. But by using absolute value up here on top, that takes care of that for you. You don't have to worry about it, because it'll make the value positive, and then an inverse cosine of positive numbers will be in quadrant 1 for sure. Let's see. All right, now to find, so obviously you'll be given some sort of plane, but the other one is the XY plane. Is we're raising it from the XY plane. So they're choosing to use our standard unit vector k. So obviously k, which goes, essentially the same direction as z, is going to be normal to the XY plane. So we use k. K is the vector 0, 0, 1. So when we do, and n is the normal vector to whatever the plane that's given. So you're taking the absolute value of n dot k over the magnitude of n times the magnitude of k. Well, the magnitude of k is always 1 because it's 0, 0, 1, so it has a length of 1. So that's why it disappears and it's not here anymore. So all you really have to do is n dot k, absolute value of it, over the magnitude of n. Then, of course, to find theta, we'll take cos inverse of all this right here. So a lot of times, sometimes people get confused by that. What happened to the k? But this is the reason why here. K is 0, 0, 1. Magnitude of it's 1. Therefore, it disappears from the formula. I mean, you can leave it there, but it's just going to be a 1. That's going to go away anyway. So once you kind of wrap your mind around that, then we are good here. This is not too bad. Just looking ahead here. Find the angle of inclination of a tangent plane. So what we have to do, I said they were going to give us the plane. Well, maybe not. They're actually giving us the information to calculate the plane. Then we can find the angle. So they didn't give us the plane, but we just learned how to get a tangent plane. So let's do that. So the gradient, pretty easy of this. It's going to be the derivative of this will be 2y respect to x, 2x respect to y, negative 3z squared respect to z, Put in the 0.222. I'll get 4, 4, negative 12. So I'll dot that with 0, 0, 1. I'll get negative 12. Then all I need is the magnitude of n. I pulled out a common 4 right here, so it left 1, 1, negative 3. So when you square it, you get 1, 1, 9. So it's 4 square root of 11, which I didn't have to simplify that. But anyway, so to find theta, we take the inverse cosine of the absolute value of negative 12. See, unlike the angle between two vectors, that doesn't have the absolute value formula there. We got to do it here because, like I was saying, this is what's going to keep it between 0 and 90. So that's makes that positive 12. 12 over 4 is 3. So we take inverse cosine of 3 over square root of 11 and make sure we're in degree mode here in your calculator. And I get about 25.24 degrees. So let's look at the graph and see what we have. 25.2. Yeah. That's kind of hard to say. Looks like I just graphed the red one's the XY plane, and then the blue one is the one that we just created. So there I'm showing you the smallest angle right there. That's what's 25.2 degrees. See, I just use Z, just means it graphed the XY plane. All right. All right, a little interesting example to kind of wrap this up, I guess, is we're going to take this function and find the points on the surface of where the tangent plane is going to be horizontal. Well, interesting. So what we're going to do is we're going to set fx and fy equal to 0. Any normal vector to a horizontal tangent plane is going to be of the form 0, 0, z, because it's going to be going just straight upward. An example of that's the xy plane itself. But any horizontal plane is going to have the equation z equals some sort of number, because it's going to be flat with just a height, positive or negative for z, no x or y. And like I said, the normal vector sticking out of it's going to be 0, 0, some number z. Let's take a look at this. So look at the partials. Okay, this is probably easy enough. So it'll be 8x plus 4y plus 8. I figure by now you probably should be pretty sharp on partial derivatives, especially one that's easy. So y will be 4x here, makes that negative 4y, makes this negative 5. And then I had to bring the z over to make it implicit right here. So I brought the z over, made that negative z. So the fz will be negative 1. So I need to find out where fx and fy equals 0. So we have a pair of equations here that we take these two and set them equal to 0, and it's pretty, you can use like substitution or elimination, and kind of worked out already without having to manipulate it that the y's would cancel automatically without having to do anything to it. So I get 12x plus 3 equals 0, which means x equals negative 1/4. Then I can plug it back into either equation and solve for y. So now we have this point, or x and y, which means we can then, I guess, find the points. Well, I guess I would specify if we wanted to, make sure that we needed the z. You could argue that the xy is good enough, but I'm actually plugging it into this function then and coming up with the value for z. What you can do in the calculator. So at this point, negative 1/4, negative 3/2, negative 5/4, the tangent plane should be horizontal. Hard to tell there, but there it is. And the equation of it's going to be z equals negative 5/4. It's kind of hard to tell from this picture, but where that dot is, you can see where the dot is. It's underneath that curve, and then the tangent's going to be perfectly flat right there. So like I said, we basically had to figure out at what point you were going to generate a 0, 0, z vector. In other words, once you knew you had a normal vector that was 0, 0, z, you knew that means the vector's going straight up, and then that means the plane had to be horizontal. Yeah, I should have probably eliminated some of this picture, but that's okay. Alright, well that concludes this video on tangent planes and normal lines.